Good morning, everybody. Today we are going to finish your chapter 12 about the intermolecular forces. Last time we did mention their different phases, solid, liquid, and gas. Between the different molecules and within a molecule, you are going to find two different forces. One is called attractive force. Another one is called repulsive force. You have your attraction and repulsion. Regarding the attractive forces, we can also distinguish them into two different groups. One is called intermolecular forces, another one called intramolecular forces. The intermolecular forces is also known as the bonding forces. Also in the last previous class, so I listed the different bonding forces in a table, and then you are going to see a table showing you different types of bonding forces and also the model, the basis of different attractions, as well the energy size and the examples. About the intermolecular forces, so we need to know, number one, the intermolecular forces is a non-bonding forces. Intermolecular forces can be found between different molecules. Usually the physical behaviors of each phase of your matter is different. The reason is the difference in the intermolecular forces. The reason also for the intermolecular forces is the strength of these forces from state to state will be different. We also mentioned 6 different types of intermolecular forces. So what we are going to do today, we are going to predict the types of intermolecular forces between the different molecules, and then based on these different intermolecular forces and also bonding forces, you can identify the key bonding and intermolecular forces to predict the higher or lower boiling point for the different compounds. So we have 4 different groups. The first group is magnesium chloride, phosphorus trichloride. You have 2 more different organic molecules, and you have 2 different alcohols. Also, you have 2 different hydrocarbons. What's our plan? Our plan will be, point 1, you are going to examine the formulas and the structures to find the major differences. For example, in this group A, you have an ionic compound and a covalent compound. So you have different types of bonding forces. If they are both the organic compounds, like B, C, and D, 3 groups, what you are going to examine? You are going to find whether the molecule is polar or non-polar. If you have nitrogen, oxygen, fluorine in your molecule, is any of these atoms bonded with your hydrogen directly? And if you have the same molecule or the similar formula, such as methanol and ethanol, you are going to determine the molar mass. If you have another 2 molecules, they are the same in terms of chemical formula, C6H14. They have the same molar mass. You are going to determine the shape and its symmetry. Here is several key points we need to know. Bonding forces are stronger than non-bonding forces. Your intramolecular forces are always 10 to 100 times stronger than your intermolecular forces. Your ionic bonding stronger than covalent bonding. If you find your hydrogen bonds between different molecules, hydrogen bond is a strong intermolecular forces. Hydrogen bond is a type of dipole-dipole intermolecular forces. And then if you have a molecule, they are not polar molecule, you are going to determine the London dispersion, So you found the polarizable electron cloud attraction. This London dispersion will be very important. And also you need to find the symmetry. If they are highly symmetrical, the attraction will be stronger. So here is our solution. For the group 1, group A, magnesium chloride. So you have your ionic bonding forces. Your phosphor trifluoride, you have a molecule which is a polar molecule, which is a covalent bonding. So therefore, for this covalent bonded molecule, covalent bonding generally speaking weaker than the ionic. And the intermolecular forces will be dipole-dipole attraction. So therefore, ionic compound has a very high boiling point. Magnesium chloride, the first molecule, has a higher boiling point than the PCl3. Group 2, CH3NH2 and CH3F. Both are organic compound, both are polar molecules, and they have the same molar mass. If you calculate it, they have the same molar mass. In your CH3NH2, this is a methylamine. This molecule has a covalent bond between nitrogen and hydrogen. Your hydrogen directly bonded to your nitrogen. Therefore, you may consider hydrogen bond. So this is how you are going to show the hydrogen bond between two molecules. In your CH3F, central atom carbon bonded to fluorine and bonded to 3 hydrogens. You are not going to find the hydrogen-fluorine bond. No hydrogen-fluorine bond formed. Therefore, this molecule is going to be attracted to each other. So this is called fluoromethane through the dipole-dipole intermolecular forces. Hydrogen bond is stronger. Therefore, this CH3NH2 has a higher boiling point than fluoromethane, CH3F. Group C. You have one molecule, CH3OH, second molecule, CH3CH2OH. The first molecule is called methanol, second one called ethanol. These two molecules are polar molecules. Both have the covalent bond oxygen and hydrogen, hydrogen and oxygen, oxygen, hydrogen. So you are going to find both polar molecule form hydrogen bonds. In this case, what's the major difference? The major difference will be a molar mass. The one has bigger molar mass will subject to the stronger London dispersion. Therefore, the second molecule, ethanol, has a higher boiling point than methanol. The very last group, D, you have hexane. Hexane has a formula C6H14. You form a straight line. So we call it a cylindrical molecule. And you have a second molecule called 2,2-dimethylbutane. So you have 4 carbons on the same line. You have 1 branch, 2 branches on your second carbon. Therefore, your 2,2-dimethylbutane molecule has 2 branches. Meaning the cylindrical hexane has a higher symmetry. The intermolecular forces, which is the London dispersion, this dispersion, so is higher. So your 2,2-dimethylbutane, imagine you have 2 branches, so the attraction will be lowered. Therefore, your hexane has a higher boiling point than the 2,2-dimethylbutane. So again, in this case, your London dispersion is the major deciding factor. So we are going to do a little double check, fact check. So your actual boiling point is already measured. Magnesium chloride 1412 Celsius, PCl3 74. So CH3NH2 negative 6.3, the other one is negative 78.3. Ethanol, I think is 46 Celsius. The methanol is 78.5, hexane 69, the second one 49.7. What our prediction is in alignment, agrees with the actual boiling point. For almost all of the liquids, they have three properties because of the existence of the intermolecular forces. The first physical properties for the liquid, for the fluid, is called surface tension. The surface molecule, for example, this H2O, this surface molecule subjected to the net attraction towards to the bulk. So towards the bottom, downward, so you are going to find the net attraction of this water molecule. This net attraction causes a liquid surface, and you want to decrease the surface area as much as possible. So this liquid surface is resulted from the net attraction of your water molecule. What is the net attraction? What's the attraction between water molecules? We already know the water molecules are attracted to each other through hydrogen bond. So this hydrogen bond will be the deciding point. In the interior molecule is attracted by the other molecules from three-dimensional. And then this molecule in the middle does not experience or was not subject to the net attraction. All these attractions cancelled out. The surface tension is defined as the energy required to increase the surface area of a liquid. The stronger this surface tension is, the stronger the attraction is. So stronger attraction resulted into the higher surface tension. Water is one of them. The second important property, so we are going to discuss, called capillary. So before we move into the second property, I want to mention these values. So you see you have diethyl ether. This ether is commonly used as an organic solvent, diethyl ether. So this is surface tension 1.7 times 10 to negative 2 in joules per meter squared. So be careful. If you have a different temperature, the surface tensions will be different. And also, what's the reason for this surface intermolecular forces? So I listed for everybody to study. You can see, so the surface tension between water molecule and water molecule is very strong, much higher, but in the same magnitude, 10 to negative 2 joules per meter squared, because of the hydrogen bond, which is is weaker. If you have liquid mercury, this surface tension is very strong. The reason is metallic bonding. Metallic bonding is ranging from 75 to 1100 kilojoules per mole. Your hydrogen bond is about 25, 40 to 40 somewhere kilojoules per mole. Is 1/10 or 1/100 of the metallic bonding. So again, if you have mercury, which is a liquid, surface tension is much stronger. The second property of the liquids or fluids is called capillary action. The capillary action meaning your liquid climbing up against the gravity. you have two possibilities. The first possibility, so we call it concave formation. If you add your water molecule into your glass wire, into the burette, which is a very narrow, thin tube. In this case, because of the coercive attraction between water molecule and the silicon dioxide is a chemical composed of your glass wire, and then your water molecule, they attracted to each other through hydrogen bond. Your silicon dioxide and your water molecule, they attracted to each other through a very strong dipole interaction. This coercive force and adhesive force, so you do the comparison. The interaction between water and the silicon dioxide, SiO2, very strong. Therefore, your water climbing up, you are going to see a concave. You see the meniscus curved down. On the other hand, if you have your mercury, liquid mercury placed into the very thin narrow tube, such as your thermometer, you are going to see mercury curved up. We are going to find a convex. Your meniscus will be convex shaped, meaning mercury displays a convex shaped. The reason is between your mercury and the mercury, you have that coercive forces, which is from metallic bonding. And your mercury and the silicon dioxide, they have very, very negligible adhesive forces. Therefore, your mercury climb up by itself is not climbing along the glass wire, but on the other way. So you see a convex. When you read the meniscus, remember you have two types. One is called concave, another one called convex. For the concave, you read the bottom of the tangent to the bottom of your concave. When you read the convex, you read the top tangent to the top of your convex. So that's another important capillary property. The very last property we call viscosity. Viscosity is the resistance of a fluid to flow. Your fluid wants to flow, so they are hooked up through intermolecular forces, cannot move freely. That resistance is called a viscosity. Viscosity for the same substances can be varied very differently by the temperature. Your viscosity is going to be determined, affected by the nature of the molecule, by the nature of intermolecular forces, and also by the different temperatures. I listed this one is for water, the viscosity for your water, 20, 40, 60, 80 Celsius. You see the viscosity decreases with the temperature increase. The reason is when you increase the temperature, your kinetic energy will be increased. So the kinetic energy pulling the water molecules apart, far away from each other. Therefore, water molecule easily to be flowing. So you have lower viscosity. Your viscosity has a unit Newton second per square meter. Followed by, I listed several examples about the heat of vaporization and the heat of fusion for some commonly used molecules. So this orange colored value is the enthalpy change of your vaporization. This lighter green color, so this is a 1.3, this is for argon 1.3 kilojoules per mole. That's representing the enthalpy change for your fusion. So if you take a look, your water very high, ethanol pretty high. As long as you increase the polarity or you form hydrogen bonds, it tends to have higher heats of vaporization and fusion. On the other hand, your mercury, because mercury bonded together or linked together through metallic bonding, so that's very different from other liquid. And also showed you how the phase changes occurs, and also during the phase changes, so how the heat is going to be transferred. So that's